lecture, I explained common emitter configuration of a transistor. In this lecture, we will plot input and output characteristics of common emitter transistor. This is common emitter configuration because emitter is common to the input side and to the output side. We are using NPN transistor in which VBB and VCC are the biasing potentials. I will write this down. VBB and VCC are the biasing potentials. VBB is used to forward bias the emitter base junction, and VCC is used to reverse bias the collector base junction. IB is the input current and IC is the output current. The input voltage is VBE and the output voltage is VCE. Generally we have the series resistance here, but for simplicity I have not included the two series resistances in the circuit, and in this scenario VBE is not equal to the forward biasing potential VBB, and VCE is also not equal to the reverse biasing potential VCC. So VBE is the input voltage, not VBB, and VCE is the output voltage, not VCC. In input characteristics of common emitter transistor, we need to plot the graphical relation between the input current IB and the input voltage VBE for the different values of output voltage VCE. So we have to plot the relation between the input current IB versus the input voltage VBE, for different values of output voltage VCE. We can also consider the NPN transistor as two diodes connected back to back. So it will look something like this. This is the first diode. This is the second diode. And you can clearly see the input current IB is the current through the second diode, and VBE is the voltage across this second diode. This diode is forward biased, so we have the forward bias characteristics of diode as the input characteristics of common emitter transistor. But the important thing is the variation in characteristics due to the output voltage VCE. I will revise this quickly. The input characteristics of common emitter transistor is similar to the forward bias diode, because you can see the input current IB is current through the forward bias diode, and VBE, the input voltage, is voltage across this forward bias diode. But the important thing is the variation in characteristics because of VCE, the output voltage. I will quickly draw the forward bias characteristics of the PN junction diode. The x-axis is for VBE, this is in volts, and the y-axis is for IB, the input current, this is in milliamps. And you already know how the forward characteristics of the diode looks. Initially the current is 0 when VBE, the forward biasing potential, is very small. Then current starts to increase like this with increase in VBE, and once VBE is greater than the barrier potential, when VBE is greater than the barrier potential, there is exponential rise in the current like this. So this is the forward bias characteristics of PN junction diode. The next thing is the effect on characteristics because of the output voltage VCE. I am considering the silicon diode, so the barrier potential is equal to 0.7 volts. In order to find out effect on characteristics because of the output voltage VCE, we need to revisit the early effect or the base width modulation. We have already discussed base width modulation in the common base presentation. This is emitter region, this is base region, and this is collector region. I am considering NPN transistor in active mode, and in active mode emitter base junction is forward biased and collector base junction is reverse biased. So base is at the lower potential and collector is at higher potential, and the voltage across the collector base junction is equal to VCB, and because of this, width of depletion layer will increase and it will penetrate more in base region because base is lightly doped, and you can clearly see the penetration of depletion layer is more in base region. Let's say width of depletion layer in base region is equal to W and the metallurgical width of base is equal to WB. Width of this region with no penetration of depletion layer is W effective, I am calling this width effective width because recombination of majority charge carriers will take place only in this region. From here we can see W effective is equal to WB minus W, and VCE, the output voltage, is equal to VCB plus VBE. VCE is equal to VCB plus VBE, and if we increase VCE, VCB will also increase. From here you can see on increasing VCE, VCB will also increase, When VCB increases, the width of depletion layer will also increase and there will be more penetration in base region because it is lightly doped, and W will increase. And from here you can see when W increases, W effective will decrease because WB is constant, it is metallurgical width of base, so W effective will decrease. So this is what happens in case of early effect. This is what we call as base width modulation. And now we have to see the effect on input current. When W effective decreases, this means region where recombination takes place decreases, and because of this recombination will decrease, the electrons emitted from emitter will not recombine with the holes in base region, and this will reduce the base current. IB, and the base current IB is the input current, right? So on increasing the output voltage VCE, the base current or the input current decreases. Vice versa is also true. On decreasing the output voltage VCE, the input current IB increases. Now we can easily complete the input characteristics of common emitter transistor. On decreasing the output voltage VCE, the base current or the input current IB increases like this. Let's say this characteristics is for VCE equal to 10 volts and this characteristic is for VCE equal to 1 volt. So on decreasing the output voltage VCE, the input current IB increases. This is in microamps, and this is the final input characteristics of common emitter transistor. The next thing is the output characteristics. Output characteristics is the graphical relation between the output current IC versus the output voltage VCE for different levels of input current IB. For different levels of input current IB, the x-axis is for the output voltage VCE, this is in volts. The y-axis is for the output current IC, this is in milliamps. We already know IC is equal to beta times IB plus beta plus 1 ICBO. When base current, the input current, is equal to 0, this implies the collector current or the output current is equal to beta plus 1 times ICBO. So when base current or input current is equal to 0, the collector current is equal to beta plus 1 ICBO. So we have small current, which is equal to beta plus 1 times ICBO, or it is equal to ICEO when the base current IB is equal to 0 milliamps. This small current is the leakage current in the common emitter configuration, and you can clearly see this equation is independent of output voltage VCE. It clearly depends on the input current IB and the leakage current. The leakage current part is constant, so it depends on IB. This statement is not 100% true. I will explain why. First, we will complete the plot for different input currents. If we increase IB in equal interval, IC will also increase in equal interval. You can see when IB is equal to 0.1 milliamps, IC is equal to 5 milliamps. When IB is equal to 0.1 milliamps, IC is equal to 5 milliamps. And when IB is equal to 0.2 milliamps, IC is equal to 10 milliamps. When IB is equal to 0.2 milliamps, the collector current IC is equal to 10 milliamps. We can easily calculate the amplification factor, the current amplification factor, beta. It is equal to delta IC divided by delta IB, small change in the collector current divided by small change in the base current. Delta IC is equal to 10 minus 5, and delta IB is equal to 0.2 minus 0.1. When you solve this, you will have 50. So beta, the current amplification factor, is equal to 50 for this characteristics. And you can see the slope is not equal to 0. The slope is not equal to 0 because IC also depends on VCE due to the early effect. We know VCE is equal to VCB plus VBE, and if we increase VCE, VCB will also increase, and when VCB increases, the effective width of the base decreases, and this will decrease the base current, and when base current decreases, the collector current will increase because more electrons emitted by the emitter will now collect to the collector. So collector current will increase and base current will decrease on increasing the output voltage VCE. So the collector current not only depends on the input current IB, it also depends on the output voltage VCE. Now we will solve one problem. This is very interesting problem, and in this problem, this region is region A, this region is region B, and this region here is region C. In column 1, we have region A, region B, and region C. In column 2, the first entity is saturation region, the second entity is cutoff region, and the third entity is active region. Now pause the video and try to match the correct options. I hope you have your answer. Now I will solve this problem. Region B is active region because in this region there is amplification of input signal. For example, when IB is equal to 0.2 milliamps, the output current IC is equal to 10 milliamps. So there is amplification of input signal in this region. That's why region B is active region. Region B is active region. Now I will find out what type of region is region A. For this I will consider the NPN transistor as two diodes connected back to back. This is the first diode and this is the second diode. If I consider the active mode of operation, then the collector current IC is having this direction and the base current IB is having this direction. This is when the transistor operates in the active mode, but we have to find out what type of region is region A. For this I will try to find out direction of collector current IC and direction of base current IB. You can see VCE is reversed. VCE is now minus VCE, and we already know VCE is equal to VCB plus VBE. VCE is negative, so we can say that VCB is equal to minus VCE minus VBE. So VCB is negative. VCB is the reverse bias potential, and now it is negative. This means VCB is now forward biasing forward biasing potential, and the direction of collector current will now change. This direction is similar to the direction of arrow in the diode symbol. So this diode is also forward biased like this diode, and this happens in saturation region. So region A is saturation region. So the region in which VCE is negative is saturation region. But what about this region? This is also the part of saturation region, but VCE is not negative in this region. You can see VCE is greater than 0, but still this region is part of saturation region. I will explain why. You can see VCE is very small in this region. VCE is very small in this region, just greater than 0, and we have VCB equal to VCE minus VBE. When VCE is very small, VCB is negative. This means reverse biasing potential is not strong enough to reverse bias this diode, and the diode will remain forward biased. Because of this, this region is part of saturation region. Now we will find out what type of region is region C. In this region, you can see IB is less than 0. The base current is less than 0. So the direction of base current will now change, and the direction is opposite to the direction of arrow in the diode symbol. So this diode is now reverse biased, and you can see in this region VCE is much greater than 0. Because of this, VCB can easily reverse bias this diode. So this diode is also reverse biased. Both the diodes are reverse biased in region C, and this happens in cutoff region. So region C is cutoff region, and this is our answer. I hope you now have better understanding of active region, saturation region, and cutoff region. In the next lecture, I will explain common collector configuration of a transistor. So see you in the next one. Last type of transistor configuration is common collector configuration. You can see in this configuration, collector is common to the input side and to the output side. Collector is common to the input side, and it is also common to the output side. VBB and VEE are the biasing potentials. IB is the base current, IE is the ammeter current, and IC is the collector current. We are using NPN transistor in active mode. Because of this, ammeter base junction is forward biased and collector base junction is reverse biased. We can also represent the common collector configuration using the symbol of transistor. I will quickly draw the symbol of transistor. We are using common collector configuration. That's why collector is common. This is ammeter. For NPN transistor, this is the direction of current. This is base. This current is base current IB. This current is ammeter current IE, and this current is the collector current IC. The input voltage is VBC, and the output voltage is VCE. VCE is equal to VBE plus VBC, and the input current is IB, the output current is IE. In case of output characteristics, we plot the graphical relation between the output current IE and the output voltage VCE for different values of input current IB. So we have the graphical relation between the ammeter current versus voltage VCE for various levels of base current IB. Now there is one very important thing that we are going to conclude. We know IC is equal to alpha times IE. Alpha is from 0.95 to 0.98, which is nearly equal to 1. So we can say that the collector current is nearly equal to the ammeter current. So we can replace this ammeter current with the collector current. And if you remember the last presentation, the graphical relation between the collector current IC and the voltage VCE for various levels of base current IB is nothing but output characteristics of common emitter transistor. So for all practical purposes, the output characteristics of common emitter transistor is similar to the output characteristics of common collector transistor. This is very important point. The next thing is the current amplification factor in common collector transistor. The current amplification factor is denoted by gamma. The current amplification factor is denoted by gamma, and it is ratio of change in emitter current to the change in base current. It is equal to ratio of change in emitter current, the output current, to the change in base current, the input current. We already know the emitter current IE is equal to the collector current plus the base current, and the collector current IC is equal to alpha times IE plus ICBO. This is equation number 1 and this is equation number 2. I want to see how output current, that is emitter current, varies as function of input current, that is base current. I will use these two equations, and by using them I have IE equal to alpha times IE plus ICBO plus IB. I got this by substituting the value of collector current in the first equation. I can further simplify this as 1 minus alpha IE equal to IB plus ICBO. Now I will divide both the sides, the left hand side and the right hand side, by 1 minus alpha. So we have IE equal to 1 divided by 1 minus alpha IB plus 1 divided by 1 minus alpha ICBO. 1 divided by 1 minus alpha is the current amplification factor in the common collector configuration. This means IE is equal to gamma times IB plus gamma times ICBO. So this is what we have in common collector configuration of a transistor. In the next lecture, I will derive the relation between alpha, beta and gamma. So see you in the next presentation.